chapter 19 from the OpenStax textbook. This is the chapter summary. So let's just flash back for a second here. What did we do in the last chapter? It was really just about this. It said that if you have charges make electric fields, and we can calculate the electric field, the magnitude of electric field due to a point charge. It's Q over R squared, so R is the distance from the charge to where you want to find the electric field, and K is a constant. K, I should write it down. K is, they put before not 8.99 times 10 to the ninth. I actually like 9 times 10 to the ninth Newton meters squared per Coulomb squared. Either one is going to be fine with me. That's a 9. I barely got in there. Sorry. There. Okay. The other thing that we saw was that if you put a charge in an electric field, then it will experience a force F, and the value of that force is just Q times E. There was also the force between two charges, but that's the main idea. Okay. So in this chapter, really the key is about, I'm going to write it down, electric potential. And this is most commonly called voltage, even though that's weird. It would be like taking this meter stick and saying I'm going to measure distance, and it's going to be called meterage, right? Because I'm using units of meters, so it's meterage. What's the meterage? How meterage tall are you? Well, I'm 1.7 meterage tall. Meters. Okay, I'm just being funny. But that's true. But voltage is something that we're going to talk about. People use it in a way that probably shouldn't be. But that's what this whole chapter is about. Now, let's take a jump back to the last semester. You took Physics 1, and I certainly hope that you covered the work energy principle. So the work energy principle says that this work is the change in energy. And we can define work for a charge, for a force. I'm going to write the simple definition of work. Work is F dot delta R, or F delta R cosine theta. So this says if I go from point A to point B right down here, here's A, here's B, and this is my displacement, delta R, it's a distance, and I have some force, F, then that force does work. And the value of that work is the dot product between those two vectors, which I'm not going to go into right now, but it is. We can also calculate that as a magnitude of F times the magnitude of the displacement times the cosine of the angle between them, theta. So that was work, and work changes the energy of a system. I know there's a lot there. We're talking about a lot of stuff, but it's so important. It's one of the big ideas in the first semester of physics. Now, if the force is not constant, or if you take some weird path, then it gets a little bit more complicated. And then what is energy? Well, you probably saw things like kinetic energy, 1/2 mv squared. You probably saw something like gravitational potential energy. And they like to write this in the book as PEG, which would be mgy. And so if you have a system that does work on the system and you get this change in energy, it could be change in kinetic, it could be change in gravitational potential energy, it could be a number of things. Okay. And that's what we're going to be talking about today. So that's why I'm reminding you about that. Let's just flash back really quickly to gravitational potential energy because it is important. This comes about because you can say that if gravity does work going from here to there, and it does not depend on the path I choose, it only depends on the endpoints, I can turn it into a potential energy. So really, the potential energy, I like to call this UG. A lot of places call it U. So the gravitational potential energy is actually negative the work done by gravity, mg delta y. That's going to be the change in potential energy. And that negative is because really we're doing the work done by gravity, and it's on this side of the equation. We move it over to the energy, and it becomes negative because you move it to the other side, it becomes negative. That's gravitational potential energy. Okay, well, it turns out that you can do that for any conservative force. There's a little bit of glare. Is that too bright? That's a little bit better. Right down over here. Okay. Any conservative force where the work done does not depend on the path. And it turns out that the electric force is conservative. So that means that I can write the electric potential energy, and the book writes this as PE, or I'll call it U. This is actually a change in. Change in potential energy is equal to the change in potential energy. That's the way I like to write it. And it's going to be negative Q E delta R cosine theta, just like that. Where E is the electric field, delta R is the displacement, theta is the angle between those, Q is the charge, and there's a negative sign there because if I'm moving in the same direction as the electric field, I'm going to decrease in electric potential energy. Now I can take this equation and divide both sides by Q, and I get delta UE over Q is going to be negative E delta R, that's a cosine theta. And this is the potential energy per unit charge, and we call this the change in potential V. So we have two things. I'm going to write this out. UE is electric potential energy. V is the electric potential. And I know it's very confusing because they both have this electric potential, but one's an energy and one's not. That's V, and the units for electric potential are volts. The units for electric potential energy is the same as other energies, joules. Okay, so we have electric potential energy in joules, electric potential in volts, and it's the potential energy per charge. It does get a little confusing, but I think you'll be fine with it after a while. Now let's just talk about how we can use electric potential energy with the work energy system. The work energy principle, I'm sorry. So just as a reminder, most of the stuff's from physics semester 1. The first thing that we always want to do, and a lot of textbooks aren't really clear about this, is to choose our system. Okay, so if I have two charges and the charges are my system, then I want to think about what forces do work on the system. So imagine I have some system of charges. That's my system. And then I want to see what interacts with that whole thing. And a lot of times we'll say the work done on that system is 0. If that's true, then I'm going to say the change in energy is 0 because the work is a change in energy. And this could be written as E2 minus E1 equals 0. So that's the change in energy. The final energy minus initial energy is 0, or E2 equals E1. So this is what you'll see a lot of times when we talk about conservation of energy. I don't know why I'm writing it out, but I am. So conservation energy says that if there's no work done on the system, the initial energy, the final energy are the same. And we can use that for a lot of things. Now that initial energy could be something like K2 plus U2 equals K1 plus U1. So it says that if I have an object moving in an electric field, then I could have a potential energy at the beginning, a potential energy at the end, and that would correspond to a change in kinetic energy to make everything work out. Again, these will make more sense, 1, reading the textbook, 2, doing some practice problems. But I just want to remind you of the stuff that we did before in the previous semester of physics. I do need to say one other thing, 2 other things. One is that a lot of times we'll talk about potential. We'll talk about potential energy. But those are not real. what really happens is a change in potential energy, right? Because work depends on the change in energy, so it's really a change that matters. So when we talk about potential, what we're doing is setting the other one equal to 0. We're saying potential with respect to 0, but we pick where that 0 is. We do the same thing with gravitational potential. Where is the gravitational potential energy 0? It doesn't matter. I could pick it to be right here. I could pick it to be down here. I'm going to get the same result because my equations only have a change in potential. So it's fine. The other thing that comes up a little bit, it was just in one of the examples I want to remind you when we're talking about energy, we also have power. And this we'll use again later. And this is the change in energy with respect to time. It's how fast you use or get energy. And so this is going to be in units of joules per second, which is equal to a watt. Okay, and I'm only saying that because it comes up, and it will come up again. So we have energy in joules. We have electric potential in volts. I do want to say one other unit because it does come up sometimes. Let's say 1 eV. Oh, let me write this as. So remember that the change in potential energy is equal to Q times the change in electric potential. So that's volts. That's volts. Volt. And the charge is in coulombs. And the energy is in joules. We have another unit that's very, very interesting, and it's called, it looks like this, EV, and it stands for electron volt. It says volt, but it's a unit of energy. This is the amount of energy that one electron gets by going through 1 volt change in potential. So delta U is 1 electron, which is 1.6 times 10 to the negative 19th coulombs times 1 change in potential volt. So if I do that, I get 1.6 times 10 to the negative 19th joules is equal to 1 EV. So the electron volt is really useful when we're talking about super, super, super tiny amounts of energy, and it happens when we're talking about electrons and atoms, stuff like this. So you'll see this unit come up quite a bit in other science courses. It's very useful, and it's very, very common, and it's cool, right? Because you can say EV, and no one knows what you mean unless they're cool too. So it's like a trick to make sure that we all know who's who. It's like a sign. Okay, so in general, we can write the change in potential, electric potential, if I have the electric field. So I can say delta V, if the field is constant, is negative E delta R cosine theta as a vector thing, and I don't think they really talk about this, but I'm going to write it just in case. It's negative the electric field dot, the dot product, delta R, because that's a vector and that's a vector. So electric field is a vector, and so is displacement, but when I do this operation, I get a scalar. Okay, so that's important. The change in potential is a scalar quantity. Well, what if I know the change in potential? Can I go the other way and find the electric field? And you kind of can. You kind of can. Okay, and the book actually wrote this wrong. If I know the change in potential and the displacement, I can find, the problem is the electric field is a vector. So actually I get the x component of the electric field is negative the change in potential divided by the change in x position. The y component of the electric field is negative the change in potential with respect to y. Okay, so you have to do it twice, and then you can get the x component, the y component. You have the vector value of the electric field. And they just said E is negative delta V over R. And either the electric field has to be constant, or this has to be super, super, super tiny. And if you let it, the delta x go to 0, you actually turn it into a derivative, which is what we do in calculus. But this is an algebra-based course, so I didn't even say that. You didn't even hear me say derivative twice, because I did. Okay. Now, there's another special case where we're dealing with a non-constant electric field, okay? And we can create a value for the electric potential, and that's a point charge. Remember, if I have a point charge and it makes an electric field, and we can say the magnitude of that is K Q over R. Sometimes we use capital R, sometimes we use lowercase r, Q. They're the same thing, okay? That's the magnitude of the field. Now, what if I move from, let's say, an infinite distance away to some distance r away? Well, that's not an easy thing to do because the electric field changes in magnitude. I can't just calculate the change in potential. So if you do it once, you can use it again, and you'd have to use calculus, so don't worry about it. But we get this. Potential is K times Q over R. Yeah. So this is the change. This is the potential with respect to infinity. So I already said you need to say where the other potential is 0, and that would be at an infinite distance away. Okay. So that's the potential with respect to infinity, and that's the potential due to a single point charge. It does come up. If you have 2 point charges, let's call this Q1. Let's call this one Q2, and I want to find the potential right there. Well, that's R1, that's R2. It turns out that V, with respect to infinity, is V1 plus V2. I can just add up the potentials due to those things. We talked about that with the electric field, but there's a big difference. So this would be K Q1 over R1 plus K Q2 over R2. The big difference here is that the potential is a scalar value. So I don't have to worry about directions and stuff like that. Whereas if I wanted to find the electric field at this point, I'd have to find the vector value of the electric field due to this one, the vector value of the electric field right there, and then add them as vectors. So you don't have to do that when it's electric potential. There is this thing about equal potential lines, which I don't think are super useful, but I want to mention it because it's in the book. So if you have a point charge right here, and I calculate the electric field all over the space, I could also calculate where the potential is equal to, let's say, 1 volt. I'm just picking a value. And it'd be right there, but it'd also be right there, it'd also be right there. All of these points have the same potential of 1 volt. And that's an equal potential line. Everywhere on that line has the same electric potential. And then I could have another line over here that looks like this. That would be 2 volts. And then I'd have another line over here, 3 volts, and so forth. So these would be my equal potential lines for a point charge. If you've ever done any kind of hiking or anything and you looked at topographical maps are equal potential lines also, except they are equal gravitational potential. This is equal electric potential. One of the things in there is that the equal potential lines are always perpendicular to the electric field. Okay, so the electric field is like that. Okay, and then you can do it for dipoles and stuff too, but I don't think it's super important, so don't worry about that. We got a lot more stuff to do. Okay, so I'm just letting you know. Let's talk about capacitors. It may seem silly to use these here, but they're very, very important. So the main idea of a capacitor is to take 2 parallel plates with equal and opposite charge. That's one capacitor. So imagine that I have a plate right here and another plate right here. We're looking at it from the side, and this plate has positive charge Q. This side has the equal and opposite charge negative Q. When this happens, we create an electric field in the interior of the capacitor. And what's really nice about a capacitor, a parallel plate capacitor, is that this electric field is fairly constant. And this is a great way to set up a situation with constant electric fields that we can use in other situations. We define the capacitance of a capacitor as C is Q over delta V. And a lot of times they write this as just Q over V. Okay. So capacitance is the capacitance of the capacitor. Q is the charge on one plate. They're equal and opposite charges, so the total charge is 0. And V, or delta V, is the change in potential going from one side to the other. So if I hook this up to a 9-volt battery, here's my little 9-volt battery, it looks like this. Then my change in potential would be V, 9 volts. And then whatever the charge would be on there, I could calculate the capacitance. So this is in coulombs. This is in volts. And that gives me a capacitance in farads. And a 1 farad capacitor is quite large. Many times we're dealing with nanofarads, microfarads. They're usually much smaller. Okay. But this comes up a lot. This is the capacitance. It actually does not depend on the charge. If I add more charge onto one of these plates, and I get more charge on the other one too, I increase the electric field, and it increases the change in potential. So the ratio of charge to potential is still the same. The value of the capacitance doesn't depend on how much charge is on there. It's a property of the physical parameters of that capacitor. So it doesn't depend on that. And if I have a parallel plate capacitor, we can actually calculate the capacitance as epsilon naught A over D. I got that backwards. No, I got that right. So A is the area of one of these plates. D is the separation of plates. So you can see as you get plates closer and closer and closer together, increase the capacitance. Epsilon naught is a constant. So we have this K 1 over 4 pi epsilon naught. So that's that 9 times 10 to the 9th. That's where it comes from. So in this case, it's just epsilon naught. There's no 4 pi. So that's that constant right there. It's called the permittivity of free space. It pops up from time to time. But there it is, the capacitance of a parallel plate capacitor. Now, you can have other shapes of capacitors too, but the one that we're going to deal with is parallel plate capacitor because it makes constant electric fields, and we like that. Let's calculate. I want that, and I want this, and then I want to create another parallel plate capacitor. Let's look at a situation. So here I'm going to draw it way too big. So I have plus Q over here, minus Q over here. And this is a separation distance D. And that has an area A, and then I have an electric field E. Constant. And remember, C is, I'll just write this is Q over V, and it also equals epsilon naught A over D. So I knew both of those things. Now, let's calculate the change in potential based on the electric field. So if I go from, let's say, here, I can start from the negative side and go over here, I get V is going to be the electric field, negative of the electric field, times the displacement D, times the cosine of 180, right? Because E is this way, delta R is that way. They're 180 degrees apart, and that's -1. So I get V equals ED. So that's the relationship between the change in potential and the electric field. I want to find the electric field. So let's calculate the electric field, VE. And this is in the x direction, so I don't have to worry about the y. It's going to be equal to V over D. But now up here, I can solve this for V, right? So I know that V is equal to Q D over epsilon naught A. I just took that and solved for V, right? So I divide both sides by that, and I get that. if I put that in for V, I get E equals V, which is Q D over epsilon naught A divided by D. The D's cancel, and I get, a lot of times we write this as 1 over epsilon naught Q over A. And that's the electric field, and it's going to be really useful, the electric field inside of a parallel plate capacitor. It doesn't depend on the distance. If I move these further apart, that electric field stays the same, as long as they're relatively close. If you get them really far apart, it doesn't really work. It depends on the charge and the area. And then there's that epsilon naught again. Okay, so we're going to use that if we need to find the electric field inside of a parallel plate capacitor. Okay. Oh, and then there is this other one. We had the electric field, the capacitance of a capacitor like that. It's possible that I could put an insulating material in there. So if I put some material in the middle of there, it's like plastic or something like that, it would have what we call a dielectric constant, K, and the capacitance would be K times epsilon naught A over D. So we can increase the value of the capacitor by putting in an insulator in between there. So what happens is that material becomes polarized, and it changes the electric field inside of there to make it have a higher electric potential. I mean, what just gives a higher capacitance. But that's not a huge deal. I mean, it comes up a lot sometimes. Okay. Now we have some algebra to do. What happens if I have two capacitors and I connect them together? And this is, let's use a little algebration here to figure out what's going on. And we're going to look at, there's two different ways to connect two capacitors. So this first way is called series. And we'll look at this when we get to circuit too. Imagine I have a capacitor right here, and then I have a different capacitor right here. I put them in series. So when things are in series, as charge moves into it, the same charge goes to the next one. So imagine I'm charging these capacitors. So I build this one up right here with positive charges. That pushes positive charges over here, so that becomes negative. But where do the positive charges from that one go? There's nowhere else for them to go but over here. And then push charges off over here. So I get Q, negative Q, Q, negative Q. All the charges are the same magnitude. That's really important. So I need to say Q, Q. Now, could be different capacitors though. Okay. So if I want to represent this with one single capacitor, we'll call that C equivalent. We'll call this C1. We'll call it C2. What did that do? I can't remember what I did. So this also has a change in potential V1. This has a change in potential V2. So if I go across here, my total change in potential is going to be V1 plus V2. So over here, if I write that equation, my equivalent capacitance has a charge Q, and it has a potential V1 plus V2. If I use the equations over here for capacitance, I can say C1 is Q over V1, C2 is Q over V2. So if I solve this for V1, I get V1 is Q over C1, V2 is Q over C2. And if I put these two in over here, I get C equivalent is Q over V1, which is Q over C1 plus Q over C2. Now I can, let's take this and multiply both sides by this and divide both sides by that. And I get Q over C equivalent is equal to Q over C1 plus Q over C2. And the Q's all cancel, and I get the following. 1 over C equivalent is 1 over C1 plus 1 over C2. So that's how I find the equivalent capacitance if I take two capacitors and put them in series. Okay, now be careful. I have to find a common denominator here, and that's going to be 1 over the equivalent capacitance. It's not the same as C equivalent as C1 plus C2. 1 over C equivalent is 1 over C1 plus 1 over C2. And in fact, it works for as many capacitors as I want. You can do the same thing for 20 capacitors. It just keep on adding plus 1 over C3 and so forth. It's keep adding on. And that's for series capacitors. Okay, what if I have capacitors in parallel? So imagine that I take these two capacitors like this. Here's C1. C2. Now as I charge up these, I get charges on these capacitors. Q1, Q2. They don't have to be the same, right? I have this current coming in. Some of it goes up there, some of it goes down there, but they don't have to be the same. But what does have to be the same? The potential across this goes from here to there. Well, if I go from here to there, it's got to be the same thing. Okay? So the potential across these are the same, the charges are not. So I want to make this as a single capacitor, C equivalent again, and I can say C equivalent is Q over V. Okay, but I know V is the same as up here, but charges are going to be, the charge on this is the sum of those charges. So this is Q1 plus Q2 over V, which I can write as Q1 over V plus Q2 over V, because they're the same potential. And Q1 over V is C1. Q2 over V is C2. So I get C equivalent is C1, C2. And this is called parallel. We're going to look at this again when we get to circuits. So in parallel, you just add the values together to get the equivalent capacitance. The definition of parallel are things that have the same potential. Right? If the potential across this is the same as that, then they were parallel. Well, not like I said, we'll get to that again. And you can add as many of these as you want in parallel. Just add them up. Let's talk about one of the things that I like to focus on the most, in other than getting chalk all over my shirt, which I actually like to do too. One of the things that I like to focus on the most in this course is energy. And you may be asking, what do you use capacitors for? And one thing you can use them for is to store energy. And let's calculate how much energy that is. There's another very, very, very useful thing to do with capacitors, but we'll get to that later. But right now, let's talk about them as a way to store energy. If you remember those old cameras that had the flash on them, and you could hear them, the flash, maybe you don't remember this. I remember it. You can hear the flash charging up and go beep. It was a capacitor that you're storing energy in, and then you'd remove the energy very quickly to get a large flash. We can make flashes in better ways now, but that's how it used to be done. You also store energy. One of the things that can break on your air conditioner. It has an electric motor that requires more energy to start than it does to run. And so one of the things you do is to use a capacitor. The capacitor stores energy in it, and you can get it out very quickly to get the electric motor starting again too. So how much energy is stored in a capacitor? Well, let's imagine that we have a parallel plate capacitor. And let's see, I can't remember the derivation I did before. So this, I want to find the change in potential going across here. The change in potential energy is Q times delta V. Right? We defined that as a change in potential energy before. That's a change in potential energy going from one end to the other. But what's the change in potential? You could say, oh, the change in potential is V. Well, I would say this side is 0 and that side is, I'm sorry. This side is 0 and that side is V. Okay. So the potential across there is 0 to V. So the change in potential is going to be really half of that value. I'm not really happy with that explanation. Why did I do that? Let's see. So delta V is because the potential is not constant. That's why. Okay, so we can write this as Q V over 2. That's the change in potential energy. And from the capacitor, I can say C is Q over V. So if I want to replace this with V, I can. If I want to replace the V, V is Q over C, solving that. Plugging that in, I get the change in potential energy is going to be, I should put this as Q over 2C, or 1/2 Q squared over C. So the amount of energy depends on the square of the charge in there and the value of the capacitance. Now, the other thing I could do is to take this and replace the Q. So I could replace the Q and I get the change in potential energy, which is the energy stored in the capacitor, is, instead of Q, I'm going to put CV. So I get 1/2 CV times V. So that's 1/2 CV squared. So those are the two ways to find the energy stored in a capacitor. And like I said, it does become useful after a while. We can also use that to actually determine the energy density in the electric field, but we'll do that later. It's a very useful thing to do. Okay, that's it. Electric potential. I think the most important thing to summarize is this. Delta V is negative E delta R cosine theta. The change of potential depends on the electric field. Do not confuse electric field and electric potential. They're not the same thing. Okay. Also, don't forget this. That's the electric potential due to a point charge. It looks very similar to this, the electric field due to a point charge, but this has a square, and that's actually a vector, so it's right in the magnitude, and that's a scalar. Okay, I think that's good enough for now. The end, chapter 19, electric field and electric potential.